So what I want to do is I'm going to walk you through the open response part of your test. It is going to be very similar to what I've put up here on the board for you to practice. And so I'm just going to go ahead and solve the practice. You are, again, what the objective is to predict where the projectile is going to land. This is straight out of your lab write-up. You are given 8 velocities, so this is representing each time you ran the marble down the ramp and the speed was clocked by the photo gates, you recorded a speed. And so I've done that 8 times, and what I have calculated as an average speed of 1.796, hey, maybe we should just call that 1.80 meters per second. I want to find my maximum and my minimum because when we calculate the distance that the projectile is going to go, we want a range of distances. We want a minimum and a maximum, and then our best guess is where it's going to land exactly is what we're going to use the average speed for. So if I look down this list of numbers, 7.90, 7.89, this 7.80 looks like the min. All right, 7.80 1.780 looks like the min, and then the max would be 1.810 for a maximum and a minimum, and then there's my average. So then the next thing to do, we want to calculate D. Now remember D, we have to derive that equation. We're going to derive that, so you're going to go through deriver's ed right now. I'm going to teach you how to derive this equation for D. From the speed equation, here we have D and we have T, and D divided by T is equal to the speed. Well, we know the speed. What we're trying to find is D, and we can figure out T if we know the height. So let's just start with the speed equation and rearrange it for D, because that is what we're going to have to, that's what we're wanting to solve for. So D is equal to the speed times the time. Now again, the time comes from this equation. This is my free fall equation, and this says if I plug in a time here, then I know how far the object falls in free fall. But I don't really want that. I know my height. That's the height of the table, and so I want to solve this equation for T. And we've done this a number of times, and so this should be recognizable to you, that T is equal to the square root of 2 times the height times the acceleration of gravity. So really all we're doing is we're going to plug this equation for T into here so that we can get D, all right? So let's see, where can I work this out? If you'll allow me to work it out down here. Okay, so D average is equal to the average speed times our time. 1.80 times 0.44 is equal to 0.792. D min is equal to the minimum speed times the time, which is 1.78 times 0.44, which is 0.783. And the maximum is 1.81 times 0.44, which is 0.796. I want to complete my chart with these values. So the predicted D is 0.792, the minimum is 0.783, and the maximum is 0.796. Okay? Now then, how does this compare to my actual? Well, this is in meters. So that's 79 centimeters compared to 81 centimeters. I'd say that's pretty close. Okay. We could go ahead and calculate percent error. So the actual is equal to 0.81 minus the predicted. We're going to use our average value of 0.79 divided by 0.79 times 100. And I'm getting about 2.5% error. That's pretty good experimental error. All right? So I'm confident that I've done everything right here. And now I'm going to complete table 3. Here I'm just using these formulas and plugging in these values of t. Okay, having completed this table, I've got, for dx, I've got 0, 0.18, 0.36, 0.54, and 0.72. For dy, I've got 0, 0.05, 0.2, 0.45, and 0.8. So we see that we are going at a constant speed in the x direction, and we are accelerating in the y direction. Okay? If I were to graph that, I would see something like this. Okay? And that's part B of the test.